Welcome to The Explainer. So today we're diving into the absolute foundation of modern heavy engineering, shipbuilding. Before a single spark flies or a ship really starts to take shape, there's actually a ticking clock that every shipbuilder has to beat. Just picture a massive shipyard stockyard. We're talking an area the size of several football pitches, packed with thousands of tons of raw steel. The exact second that steel arrives from the mill and gets cleaned, it kicks off this desperate, invisible battle against the elements. We're going to uncover the highly specialized, kind of invisible shield that protects these ships right as they're being born.
Okay, let's get right into it. When steel first rolls in from the mill, it's covered in mill scale and rust. Shipyards blast all of that away by firing millions of tiny steel balls at the plate. But here's the catch. Once you do that, that naked steel becomes highly reactive. If it's just sitting out in a humid shipyard environment, it literally starts flash rusting within mere hours. You just can't blast a plate on a Tuesday and expect to weld it next month. Now contrast that with a plate that's been primed. It can sit out in the exact same yard, facing the exact same weather, for 6 full months and stay perfectly, incredibly clean. This wild contrast is exactly why every modern shipyard wires its shop blast plant straight into a primer spray line. Which brings us to our unsung hero of the stockyard, prefabrication primer. You'll also hear it widely called shop primer or weld-through primer out in the industry. Basically, it's a super thin coating applied instantly after shop blasting. Now, I really want to hit hard on the word temporary here. This is absolutely not the final marine paint system that protects the ship out on the open ocean. Now, its one and only job is to be a temporary bodyguard for the steel surface during the absolute chaos of the building phase. It has to survive plates being dragged around, sliced up, mashed into panels, and hoisted into massive structural blocks. So the really wild part is just how incredibly thin this bodyguard actually is, 15 to 25 micrometers. That is extraordinarily thin. To put that into perspective, a single human hair is roughly 70 micrometers thick. So this coating is literally a fraction of a hair's breadth. We're talking about a microscopic layer of defense protecting a massive 75,000-ton megastructure. It's a crazy micro to macro contrast. But, there is a very strict, uncompromising engineering reason it has to be this microscopically thin, and it sets up one of the greatest paradoxes in all of steel fabrication. And that paradox boils down to one simple question. How on earth do you weld through paint? In heavy construction, you absolutely have to protect the steel with a coating so it doesn't just rust away while it sits in the yard. But ask any fabricator, and they'll tell you that painting steel usually completely wrecks the welding process. Welding requires pure metal-to-metal fusion, right? So throwing a chemical coating right into a superheated electric arc, that's usually recipe for total disaster. Let's break down exactly what happens if you try to cut corners with just standard, everyday paint. Under the intense heat of a welding arc, conventional paint just burns rapidly. And this violent burning traps gases right inside the molten pool of steel. When that weld pool quickly cools down and solidifies, those trapped gases have absolutely nowhere to go. So they create these tiny microscopic voids or bubbles inside the metal. We call this weld porosity. And as you might guess, porosity completely tanks the structural strength of the joint. If you're building a ship that's going to battle heavy ocean waves, a weak, porous joint is literally a catastrophic failure waiting to happen. And that is exactly why prefabrication primer is not something you just pick up at the local hardware store. It is specially formulated to keep weld porosity to an absolute minimum while maintaining acceptable joint quality. It's designed to act almost like it isn't even there when the welding torch hits it. Whether a human is welding it by hand or a giant automated machine is running the bead, this primer just vaporizes cleanly. It doesn't trap harmful gases, it keeps the fumes low, and it lets the welder run a super strong, high-quality joint straight through the plate. No need to waste hours grinding paint off the edges beforehand. So how does this fit into a shipyard's massive high-speed production line? Well, it's a continuous, totally unstoppable process. First, the heavy plate comes right out of the shot blast machine. And because it just took the violent friction of millions of steel shot impacts, the plate is actually physically warm to the touch, and the bare surface is highly chemically reactive. Then, before it even gets a chance to breathe the ambient air, it immediately rolls into an airless spray booth. Automated nozzles blast the primer uniformly across both sides in one single pass. And because the plate is warm and the primer is highly specialized, it dries in literal minutes. The whole thing, from rusty, warped mill steel to perfectly blasted and primed, takes less than 5 minutes. Boom, vulnerable to fully protected in the blink of an eye. Now, what's genuinely fascinating here is the chemical balancing act required to pull off this 5-minute miracle. Think about the engineering requirements for a second. First off, it needs incredibly fast drying times, so cranes can grab the heavy plates immediately without smudging them. Second, it absolutely has to be non-toxic. When that welding arc hits, you cannot have obnoxious or dangerous fumes flooding enclosed shipyard spaces. Gotta keep the workers safe, right? Third, as we just talked about, it must be weld compatible to stop that nasty porosity. So what's the magic formula that ticks all these boxes? Zinc dust suspended in an epoxy resin. The zinc acts sacrificially, meaning it'll actually step up and corrode before the steel does, giving you that incredible temporary rust protection, while the epoxy resin glues it all tightly and safely to the steel's newly blasted rough surface. It's brilliant.
Let's take a step back and look at the big picture of what we've actually achieved here. Think about the journey. The steel is procured from the mills, carefully organized in the stockyard, flattened out in heavy mangles to remove residual stresses, shot blasted down to pure metal, and finally, coated with our 15 to 25 micrometers superhero primer. We have successfully stabilized our raw material. The steel is now this perfectly protected, flat canvas just waiting in the yard. It's totally ready for the intense heat of plasma cutters and the heavy lifting of block assembly. The epic transformation from a raw ingredient to a massive ocean-going vessel truly starts right here.
But of course, that leaves us with a fascinating new physical problem to solve. The steel is protected, sure, and as we just established, it's completely flat. But as we all know, ships aren't just boxy squares. They have these beautiful, sweeping, complex, double-curved holes. So how in the world do we take thick, cold, prime steel plates and bend them into the aerodynamic curves of a ship without completely destroying their structural integrity? Think about the sheer mechanical force and thermal control you'd need for that. It's a totally mind-bending process, and it's exactly what we're going to dive into next time. Thanks so much for joining me on this explainer, and keep questioning how the world is built.